Measures of center. So measures of center, as the sentence or the phrase explains itself, is they are used to measure the center of data. For instance, suppose that is the real number line, and we have data on the real number line. And let's say there are observations between 10 and a maximum of 50. Our objective, if observations are going to lie between 10 and 50, we want to know where the center of the data would be. Now, keep in mind, if the observations are equally likely, in the sense they are equally spaced between 10 and 50, then the center would be exactly here. But if we have more observations on one side, say I have a lot more observations here, over there, and fewer observations over here and few over there, then the center is going to lean toward where we have more observations. So the more observations pile up on this side, the center is going to start shifting. So it's no longer going to be at this point. It'll probably move somewhere over there, because majority of data points are on the left-hand side. So all these measures of center are part of something called descriptive statistics. So there are 4 measures of center. We have mid-range, mean, median, and mode. So all of these measures of center are used to find the center of the data. The simplest of them is the mid-range. So what is the mid-range? The mid-range is simply the average of the minimum value and the maximum value. Minimum in the sense the smallest observation in the data, maximum is the largest observation in the data, and we take the average, we add them together, divide by 2 to get the mid-range.
Mean takes all the numbers divided by the amount of observation. Median is the...
Okay, so the mean is the sum of all observations divided by the sample size, which is the total number of observations. Median, on the other hand, it is slightly different, in the sense median is what we call an ordered statistic. what is an ordered statistic? An ordered statistic is any statistic that is obtained after sorting the data. So in other words, we've got to put the data in ascending order, and then we would find the median. So in order to find the median, the very first step is to put the data in order. So any statistic that is obtained after sorting the data is called an ordered statistic. So I will explain how to find the median. And lastly, we have the mode. Mode simply is the most frequent observation in the sample. Most frequent in the sense, the one that repeats the most. All of these would help us find the center. Of course, some of these statistics are better compared to the others, and I will explain that in the next section. But before we get to that, we would want to know what or how to find the median, because finding the mid-range is easy. It is the minimum plus maximum divided by 2. The mean is easy. You sum all the observations and you divide by the sample size. Mode, you just look for the most frequent observation. However, median, it just requires a little bit of work, but it is doable. So mind you that finding the median and the mean for small data sets is very, very easy. But as the data set increases, in other words, if the sample size gets bigger and bigger, you have way too many observations in your sample, and it's just not feasible to do it manually. So I'm going to illustrate a manual approach to find the median, but you can only do this if you have fewer observations or a fewer number of observations. So what we're going to do is, when we have real data sets, and if they have too many observations, we're just going to make use of the calculator, and I'll show you how this can be achieved using a TI-84 calculator. So before we get to that, here is the manual approach to find the median. So, and I didn't put the mean here. Of course, we could find the mean, but I'm going to use the calculator to find the mean of the sample once I do the mid-range, median, and the mode. So the mid-range is quite easy. The data, if you observe, it is sorted already in ascending order. So we have the data in ascending order. So finding the mid-range is straightforward. We take the maximum value, 7.5. We take the minimum value, smallest value, 1.5, add them together, divide by 2. So we will have 9 over 2, which would give us 4.5. Now we need to find the median. So the median is the statistic that divides the sample exactly in half. In other words, if we have this sample, and if I declare a number to be a median, there has to be equal number of observations on either side of the median. So I'm going to illustrate this using the real number line. So 0, 1, oops. So I have one observation at 1.5, one at 2.2, one at 3.4. I have 4 of them at 4, so 1, 2, 3, 4, and 1 at 5, 1 at 6, and 1 at 7.5. Now, I have, just by looking at the previous part, the mid-range tells us the center has to be right here. Now, the median should split the observation into 2 halves. So if I wrote the data out, so 1.5, 2.2, 3.4, 4, 4, 4, 4, 5, 6, 7.5. I want to come up with a number that splits the data exactly in half. If I say that the number is right over there, that doesn't split the data exactly in half because I have 8 observations on one side, 2 on the other. If I say that the median lies over there, then I have 7 observations on the left side, 3 observations on the right. So that median cannot lie there. So what is a reasonable value for the median? If I have to split a sample of size 10 exactly in half, there has to be 5 on either side of the line or of the median. So 1, 2, 3, 4, 5. So the median has to lie between those 2 numbers. So if the median lies between those 2 numbers, I have 5 observations to the right of the median and 5 observations to the left of the median. And a reasonable value to pick a median would simply be to take the average of the 2 values, the one on the right and one on the left. If we take the average of the 2, in other words, add the 2 numbers and divide by 2, we would end up getting the median. So the median in this case is simply 4. So if the sample size is even, then So if the sample size is even, then the median is simply the average of the n over 2 and n over 2 plus observations in the sorted data. So now let's look at our example. So in our example, n is 10. 10 is definitely even. So the median is the average of n over 2, which is 10 over 2, average of the fifth observation, and n plus 2, excuse me, n over 2 plus 1, which is 10 over 2 plus 1. That would be the sixth observation. In the sorted data. So if we go back and observe what we did, so the fifth observation in the sorted data is 4, and the sixth one is 4, and we took the average of the two. So that is how we find the median. If the sample size is even, what would we do if the sample size is odd? So if we have an odd sample size, then the observation in the n plus 1 over 2 position of the sorted data is the median. So for example, let's just take a case 2, 2.5, 3, 4, and 9. The sample size there is 5. And clearly the median is the observation that splits this data exactly in half. So 3 is going to be the median, because if I select 3, 2 observations would be on the right of 3 and 2 would be on the left of 3. So the median is naturally 3. But how does it relate to the statement that I just wrote? So it mentions that it is the observation in the n plus 1 over 2 position. So n here is 5, and 5 plus 1 over 2 is 6 over 2, which would imply third position. And the key thing to note here is that the data has to be in order. And lastly, the mode is the most frequent observation. And in our case, it seems pretty obvious. 4 repeats 4 times, so the most frequent observation is simply 4. Now you may wonder, oh, the mode, the mid-range, and the median, they're all the same. Is that the case always? Yes, under certain circumstances, the mean, median, and the mode will always be very close to each other. There are cases where they won't, and that would be the next section, which will be on skewness and outliers. If you have to find the mean, we simply have to add all these numbers and divide it by 10. That shouldn't be very complicated. So let me just find the mean here also. Mean is the sum of all the numbers. So 1.5 plus 2.2, 3.7 plus 3.4 is 7.1. 7.1 plus 16, 23.1 plus 5, 28.1 plus 6, 34.1 plus 7.5, 41.6. So 41.6, that is the sum of all observations. And we divide that by 10, we end up getting 4.16. And you can see that the mean is also very close to the median and the mid-range. So this is one of those samples where things are working out really well. And the reason for that is in the picture itself. If you sort of look at the data, you could see a symmetry about 4. You have equal number of observations on either side, and majority of them lie in the middle. So I would expect the mean, median, and mode to be very close to each other. So a very good example is where mean, median, mode are very close to each other is the one that we just did. Now, how do we relate that to what we see in practice? For example, if we have a data set, could we just look at the data set and conclude if the mean, median, mode would be the same? Are they going to be different? And that is related to what we call skewness. So I'm going to consider a data set, and each dot, let each dot represent observation, an observation. So I'm going to pile a lot of observations. In other words, there are lots of observations over there. And as we go to the extreme, the number of observations decreases and gets fewer and fewer. So you can see majority of the observations are piled between 4 and 8, hypothetically speaking. And a few are on the side, let's say 12 over there, 0 over there. So things are getting piled up. So majority of the observations are between 4 and 8. So if we construct a histogram and attain what we call a density, we will get a curve of this sort. And that particular curve is sort of symmetric. And the most frequent observations are the ones that are right in the middle. If you, I'll just say that to be 6. So in the histogram corresponding to this sample, I'm saying about 6 because when we construct a histogram, there is always that class width that we need to focus. But theoretically, the mode would be 6 in this case. So when we observe a sample of this sort, this sample has 1 no skew. No skew in the sense the data is symmetric. And if we have a sample that has no skew, then the mean would be approximately equal to the median, which would be approximately equal to the mode. So let's go back to my previous example, even though it's not going to produce a histogram like the one here. But if we go to that real number line, you can see we have symmetricity in the sense we have 3 observations to the left of 4, 3 observations to the right of 4. So there is symmetry. So which is why the median, the mean, and the mode, they were very close to each other. They're not exactly the same, but they are approximately equal to each other. So the next case is where we have observations. Let's say we have a bunch of observations over here. So each observation, I'm just piling it up. So whole lot of observations between, say, 0 and 4. And as we go further, the observations get fewer and fewer, and that's what we have. And the largest observation, let's say it is about 16. So in this case, majority of the observations are between 0 and 4. And as I go farther away from 4, the number of observations decreases. So if I draw a curve, that curve is coming from a histogram. So by looking at it, we can see that majority of them are between 0 and 4, and the few observations on the right-hand side so there are a few observations which are far away from the majority of the observations. So when we create a histogram and obtain a picture of this sort is what we call right skewed sample. And typically, anytime we have a skew, there will be outliers. So outliers are the ones that doesn't represent the majority of the sample. Clearly from the picture, I can pick out 16 to be an outlier. Reason being, majority of the observations are between 0 and 4, and 16 is far away from 4, so that would be the outlier. And lastly, if we have right or positive skew, typically the mean is likely to be greater than the median, which would be greater than the mode, theoretically speaking. And that brings us to the last case, of skewness. Let's say 0, 10, and if I put a lot of observations right there, so each dot would represent an observation between 8 and 12, majority of them are piling up between 8 and 12. And as I go far away from 8 and 12, things start to thin out, and I simply have fewer and fewer observations as I get closer to 0. So if I drew a curve, that's the curve that I would have. So the majority of the observations are right over here. And the outlier is at 0. And clearly, because of the outlier, we have skew. But in this case, the outlier is on the left-hand side and it is pulling the data to the left. So here we have a left or negative skew. And there are outliers. As an example, zero is an outlier. And if the data has a left skew, mean would be less than median, which would be less than the mode. So just by looking at the histogram, we would be able to determine if the data has skew or not. And if we can identify the skew, then we can sort of, guesstimate a few things. If there is no skew, the mean, the median, and the mode would be the same. If there is a right skew, then mean is likely to be bigger than the median. And if it's a left skew, the mean has to be less than the median, which would be less than the mode, and so forth. So here is an example about pH. So the acidity or alkalinity, in other words, the basic property of a solution, is measured using pH. So if a solution has a pH less than 7, the solution, whatever it might be, it is very acidic. If it is exactly 7, then the solution is neutral. And if it goes over 7, then it is basic, it's alkaline. So there are differences between the tap water that we consume and bottled water. And here they have a sample that compares tap water and bottled water. And we want to find the mean, median, and mode for each type. And let's see if we can make an inference. So we can do this directly using a TI-84 calculator, the median and such. But the mode, we can figure it out just by looking at observations that repeat itself. So I see 2 7.45s, but 7.5 47 repeats 3 times. So the most frequent observation is 7.47 for tap water. So the mode is 7.47. For bottled water, the mode, let's see, is there something that's repeating itself? I see 5.26 repeating itself twice. And I don't see any other observations repeating itself. So the mode is 5.26. The rest we can do using the calculator. So in your calculator, TR-84, you press start, press 1, and you can enter data in list 1. So what I'm going to do is I'm going to enter tap water data in list 1, bottled water data in list 2. So for entered all tap water data, now I'm moving on to the bottled water. So 5. And so just by looking at it, we know all the numbers in the bottled data part are about 5. The tap water part, the observations that we see are about 7. So just by looking at it, we can conclude that, okay, on average, bottled water is going to have a pH less than 7. It is going to be more acidic. But you may ask me, well, if I can make a conclusion just by looking at it, why do we need to find the mean, median, mode? As I mentioned earlier, this is a small sample. Imagine instead of this small sample, someone collected thousands of observations. It wouldn't make any sense, or it just wouldn't be possible for us to look at the data and come to a conclusion right away. We need to find the mean, median, and other statistics. So now that I've entered the data, I'm going to exit, press start, over to calc, which stands for calculate, select 1, 1 more starts. Note, if you have the newer model of TI, it should have list freaking calculate. So in your case, you just enter L1 here, leave that blank, and then hit calculate, or it might say paste. If you have the older model, you can simply do 1 var start, second 1, and hit enter. And that gives me a mean of 7.5. And if you scroll down, you would see med. Med is simply the median, and that is 7.485. Second mode to exit. Oh, sorry, clear to exit. Bottled water information is in list 2, so press start, over to calc, select 1, but only this time we have to use the information in list 2. So second 2, enter, and we end up getting 5.194 for the mean. The first number that you see, X bar. And scroll down, med is the median, and that happens to be 5.22. So that's how we find the mean median. Mode, we have to do it manually. So what can we conclude just by looking at the statistics that we have? The simplest conclusion that we can make is that the tap bottled water is more acidic than tap water, because if you look at it on average, the bottled water pH was 5.19, tap water is about 7.5. So it is going to be more acidic with tap water. So part B wants to know, suppose pH of 7.10 in the tap water was incorrectly recorded as 1.70. How does this affect the mean, the median? What property of the median does this illustrate? So we're going to go back to the tap water sample. And I am going to change (7.10) to 1.7. In other words, someone made a mistake, and it is a significant mistake. They, instead of recording, or the student Emily McCarney, instead of recording the solution to be neutral, in other words, 7.1 pH, she put it as 1.7. It is extremely acidic. By all means, you can't drink water that has a pH of 1.7. But if someone made a mistake, what would happen to the statistic? We'll go back and compute the mean, median for list 1, which is the tap water data. So the mean X bar is 7.05. The median is 7.485. So what can we see? Because of the mistake that was made, the value of the mean changed. It changed from 7.5 to 7.05. But if you look at the value of the median, it did not change at all. So clearly 1.7 is an outlier. Majority of the observations in the tap water sample is in sevens, and 1.7 is clearly an outlier. So what happened when we introduced the outlier? It affected the mean, but not the median. So in short, typically, I'll put this as a remark, the median is a better measure of center because it is not affected by outliers. Now, the mean will be affected by outliers. The mid-range significantly will be affected by outliers, and mode occasionally. But the median, if we make a mistake and if we introduce an outlier, for instance, in this problem, instead of having it as 7.1, if we have it as 1.7, then the median still would not change. So that would be the answer to part B. So this is about Old Faithful, the guys in Yellowstone National Park. And apparently there's another one, it's the Old Faithful, and it represents, the data that we have represents the length of eruption for a random sample of eruptions of the Old California, or the California Old Faithful. So they want us to determine the shape of the distribution. Shape is something we talked about last time. By drawing a frequency histogram, we need a frequency distribution, and we have to find the mean and the median, and which measure of center or central tendency better describes the length of eruption. So first, we need a frequency distribution. So we did it last time. The smallest value that we see is 90. It's right over there and there too. The largest eruption time that we see is 111. So it's right over there. So we have a span about 90 to 111. So let's define our class width. I'm going to go for a class width of, say, 3. So So 90 to 93, 93 to 96, 96 to 99, 99 to 102, 102 to 105, 105 to 108, 108 to 111. And the next step is to obtain the frequency. So if something falls in the border, we will just put in one or the other. 90 to 93, so we have 1, 2, 3. So we have 3. 93 to 96, 1, 2, only 2. 96 to 99, let's include 99. So 1, 2, 3. We have 3. 99 to 102. We already counted 99, so I'm going to go for the other numbers. Let's include 102. So 1, 2, 3, 4, 5, 6, 7, 8, 8 of them. 102 to 105, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Looks like I missed 100. So I'm just going to go ahead and include that 100. So should be 9. 105 to 108. We've included 105 already, so I'm just going to go for the 108. 1, 2, 3, 105 to 108, 4, 5, 6. That is all I see. 108 to 111, since I've included 108 already, I have 1, 2, 3, 4, 5, 6, 7. And I've got 111 to 116, 116 to 119, 119 to 122. Because I have an observation of 120. So, all right, 2 observations here, none there, and 1 observation between 119 and 122. Now, keep in mind, it is very objective for us to choose the class width. If you use a different class width, for example, a class width of 4, your histogram is likely to change, but it's not going to make a huge difference. But if you picked a class width of 8, then you probably wouldn't even see a shape. So let's see what happens when we draw this graph. So I'm going to say that that is 90, 93, 96, 99, 102, 105, 108, struggling here. One 11, 113, 116, 119. And I'll just put a dot at 120 because to me it looks like an outlier. So 90 and 93, I have 3 observations. So I'll call it 2, 4, 6, 8, 10. So 3 here, 2 there, 3 again. And we have 9 between 99 and 102. 11 between 102 and 105. And we get 6 between 105 and 108. 7. Then we have 2 between anything 111 and 113. did I miss an interval? Let me look at 111, 113. So I've got to include that. So 111 to kind of messed up in my addition, my bad. So it has to be 111 to 114, 114 to 117, 117 to 120. Okay, so I guess I'll have to take algebra again. So we have included 111 already, so 112, 113, 14. I have only one. So that should be 1. 114 and 117, we have 1, which is 116. 117 to 120, we simply have 1. And now I can fill it up, so I'd have 1, 1, 1. So that's sort of the shape I'm getting. So if I, as I said, if I can't see the shape, we could, always draw a line or an outline of the graph by connecting the bars. So what I'm going to do is I'm going to simply place dots here and see if I can connect them. It is not going to be a very nice picture, but we'd sort of get an idea about the shape of the data. So you can see perhaps the data has no skew. Perhaps the data is going to be symmetric. Why am I getting a messed up picture? Because I chose a class width of 3. Had you chosen a class width of, 2 or maybe 4, you would get a different picture. So I'm going to show you how to get a shape using the calculator and then answer the question. So I've showed how to do this manually, but I'm going to show it using the calculator also. So I want to erase all the data in list 1 and list 2, which is already gone. So I'm going to enter the data that we have. So I've entered all the data now. I can exit out, press second y equals. That is going to bring up start plots. And we have to choose a histogram, but before we could do that, we had to turn a plot on. So I'm going to select 1, turn it on. And of all the options, it'll be that one. I'm going to select that option. And it just asks me xlist L1 freq. You can just leave it as is. If you created your own frequency histogram, you can put the freq in, but that might lead to a messy graph like the one I have. So I'm just going to go ahead and hit graph. And we see nothing because our range is set from -10 to 10. I believe zoom 0 should work. If not, we can just adjust the window. Our values are between 90 and 100, so I could put 85 all the way up to 125 and hit graph. And that's sort of the picture that I'm getting. It's sort of very similar to what I have, but you can see the class width that the calculator uses is slightly different from the class width that I used. But in terms of the picture, you can see it more or less similar. So it could be, normally distributed in the sense without a skew. To find the mean and the median, we can use the calculator directly. So second mode to exit, start, over to calc, 1, second 1. And I get a mean of 101.86. And my initial guess is perhaps the data could be normal, but I see a lot of weird things going on. The median is 103.5. They're not very close to each other. They're slightly off. And so which one would describe the length of eruption better in this case? The median is going to, because one of the values seems to be quite, out there, which is 120, and the same with 90. It's kind of far away. So I would say 120 seems like an outlier. Even in the graph, you can see that last bar is at 120, and that could be an outlier because it's far away from the rest of the observations. So the better statistic in this case would be the median. As always, if we have outliers, then the median is better. You look at the picture, it sort of looks like, data with no skew, but at the same time, there are observations far away from the center. So the better statistic here would be the median. So before we proceed further, I did make a change because I entered one of the observations incorrectly. The rest doesn't change. The mean happens to be 104.14 and the median is 104. And the mistake happened with the calculator and not when we created the frequency histogram. So this is a similar problem to the previous one. We are going to use a class width of 12. In other words, the classes would be 0 to 12, 12 to 24, 24 to 36, 36 to 48, and that is going to capture the maximum class. So the hours worked and the frequency. So 0 to 12, 12 to 24, 24 to 36, and 36 to 48. Between 0 and 12, we have 1, 2, 3, 4. We have about 4. 12 to 24, we have 1, 2, 3, 4, 5, 6, 7, 8. 24 to 36, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 36 to 48, we simply have 1. So if I drew this, (0 to 12, 12 to 24, 24 to 36, 36 to 48, 48 to 60, and we have frequency up there. 2, 4, 6, 8, 10, 12. Between 0 and 12, we have 4. 12 to 24, we have 8. 24 to 36, we have 12. 36 to 48, we have 1. So it looks like the data is likely to be skewed in this case. Even though it is not clearly visible, there is going to be skew. So and it seems like it would be a positive skew. And let's put it in the calculator and see what the calculator decides as a class width. So I went for a class width of 12. If I've reduced and used a different class width, my histogram is going to look different, but is it going to look better? I do not know. So it's very subjective in choosing the class width, and takes a bit of experience, requires a bit of experience to come up with the correct class width. So the data, we have 0, 0, 15, 20, 30, 40, 30, 20, 35, 35, 28, 15, 20, 25, 25, 30, 5, 0, 30, 24, 28, 30, 35, 15, 15. So second mode to exit. If we did one var starts and list one, we get the mean to be 22 and the median happens to be 25. And naturally, the median is bigger than the mean. From earlier, right skewed data, median is likely to have a value that is bigger than the mean. So that's exactly what's happening here. But to be very conclusive, we can plot the histogram. So select one, turn it on, and over to histogram, and adjust the window. If we don't adjust it properly, we're going to get funny little graph. So let me adjust the window here. 0 to 45 in steps of 5, 0 to 15. And that is the shape I get. I can adjust this a bit more. Instead of going in steps of 5, perhaps I could do 12. Maximum value is 60. And that matches, to what we have. So you can see that by adjusting the window, we can actually get a better picture. But it takes a lot of tweaking to come up with the correct class width. So let's try 8 and see what happens. Not that great. Maybe 10. So in all cases, it seems to have sort of a skew. Clearly, it is not symmetric. So it's got a skew. And there's one observation, which is 40, that is likely to be an outlier. We can't conclusively say what skew it is because it's not obvious. It could be right or left. We can't say that. We can make one more change and see what happens. Reduce the class width to 6, and we still cannot see a good skew here. So even though I said perhaps, but changing class width might help. So I tweaked it a bit, but it's still not conclusive. It seems like that 40 is pulling the data in one direction. So which is why I said positive, perhaps. Again, this is very subjective and you need a lot of data points to be very conclusive. So that's that. Recording. So Mr. Zero finds the height of all 14 students in his statistics class, and that average happened to be 68 inches. So we'll just call the average X bar of 14 students is 68 inches. And just as Mr. Zero finishes explaining how to get the mean, Daniel walks in and Daniel is late. But what we know is Daniel is 65 inches tall. Now we want to find the mean height of 15 students using what we already know. So what is the average of 15 students? The average of 15 students is simply the sum of the heights of each student all the way up to 14 students, and the 15th one is Danielle, divided by 15. Now, Mr. Zero found the average of 14 students. If I know the average, I can find the sum of the heights of those 14 students. So x bar 14 is simply x1 plus x2 all the way up to 14, x14, divided by 14. That's how we find the average. Add all the heights of those 14 students, divide by 14. We know the average at Zero found was 68. So 68 would equal to x1 plus x2 all the way up to 14 divided by 14. So if I multiply by 14 on both sides, I get 952. So the sum of heights of those 14 students before Daniel arrived was 952. In other words, that part is 952. So 952 plus Daniel's height, which is 65, divided by 15 would give us the average of the 15 students after Daniel arrived. So 65,017 divided by 15. So the new average is 67.8. So the purpose of this problem is to compute the average using the average that you know previously. So we're using the average of 14 students and the new bit of information that we got from Danielle to get the average of 15 students. So the professor graded the exams of 20 students. Now I'm going to call readable scores as x1, x2, all the way up to x19. The one unreadable score, I'm going to call it as y20. So the average of all 20 grades, the mean score of 20 students is 82, which simply would be x1, x2, all the way up to x19, all the readable scores, plus that one score that is not readable, divided by 20. And we also know the mean of the 19 readable scores is 84. In other words, is 84. So that is simply x1, x2, all the way up to x19 divided by 19. So using that, we can find the value of x1 plus x2 all the way up to x19. In other words, the sum of the 19 readable scores. So if I multiply by 19 on both sides, I would have x1 plus x2 plus x3 all the way up to x19 to be equal to 16, 20, 16, 40, I believe.
Yes.
So 1640. Now we could take that, plug it in the previous equation. So we will have 82 equals 1640 plus y20 divided by 20. And that would mean the missing value y20 would be 8220. Oops. Times 20. Oh, 84 times 19 is 1596. I'm sorry. That's odd. 1596. I forgot to subtract. Because they both can't be 1640. It means that readable score got a 0. So 1596. And if you cross multiply, you would have 1640 minus 1596. And that is 44. So the unreadable score was 44.